So good morning, everyone. Let's start with day 2 of the tuning workshop. So can you hear me? Okay, yeah, thank you. So my name is Christian Feld. I work at the Jülich Supercomputing Center in Germany. And in this morning session, my colleague Brian and I will tell you about the instrumentation and measurement framework Scorpio, and how to analyze Scorpio measurements with the tools Cube and Scalaska. So I'm going to share my screen now. Okay, screen 1. Okay, you can now see my screen. Yeah, here I'm on the tuning workshop website. So we are here at the first session. You can find the slides here online if you want to follow the slides. And I now switch to the real presentation. Okay, just a second. Oops, that was not what I wanted to do. Okay. Let's go to full screen here. Okay, so we start with Scorpio, which is a instrumentation and measurement framework. And the results of a Scorpio measurements then can be used by a variety of analysis tools. Among them is Periscope, which is a tool for online measurement analysis, which we don't cover today, but we will cover today Scalaska. And yesterday, Tau was already covered, and Vampire is also not part of this tuning workshop. But so the message here is that with a Scorpio measurement, you can use a variety of tools to analyze your codes. So Scorpio comes with an instrumenter. So this is basically to prepare your measurement. It comes with some libraries. So the libraries then create these measurement events and write them to specific output files. It also comes with a small or command line analysis tools called Scorpio Score. This is to help you to configure Scorpio measurements. So let's look at this again. Here in this performance and engineering workflow you already saw yesterday. So we are in this morning, we deal with the preparation of your program. So this basically means inserting some probes, some hooks into your application. So this is done with the instrumenter, which is called Scorpio. It's just a command line tool that you prepend before your compiler. So if you usually compile your code using FTN or MPI-CC, you just write Scorpio in front of your compiler. So it's then Scorpio FTN or Scorpio MPI-CC. And this preparation means that you recompile your code. So you need to modify your build system. This is sometimes easy, sometimes it's a little bit tricky. We come to this later. So once the preparation is done, which is usually a one-time effort, you can do lots of measurements in different configurations. So the configuration of measurements with Scorpio is exclusively done using environment variables. So in your job script, you just do an export Scorpio enable something, and Scorpio then knows what to do. And you can use, if you have a instrument executable, you can use it for several measurements, which we will also see later in the hands-on. Then with the measurement results, we can do some analysis, which we will see later with the cube tool and Scalaska. Okay. As already said, Scorpio is a tool for instrumenting your applications and for doing the performance measurements. With Scorpio, we can create several kinds of results. So the two important ones is call path profiles. So this is what we usually start with. We run an instrumented application in default mode, and it will create a cube profile, which then can be analyzed using the cube GUI tool. Once we have some experience with the first measurement, we can adjust the configuration a little bit. So usually we want to filter out some stuff that we don't need for our specific analysis. And we want to reduce the overhead a little bit. And once this is done, we can do some event-based tracing. So this will create OTF2 files, which can become quite large. So therefore, we need to configure the measurement a little bit so that everything will fit into memory. So we can also do some online profiling with the periscope tuning framework, but this will not be part of this session today. So what can Scorpio be used for? So basically for all applications that run on contemporary HPC systems. So we support MPI and SHMEM for the multiprocess communication. For threading, we support OpenMP and P-threads. So this also means C++ threads, which are based on P-threads. We support CUDA, OpenCL, and OpenACC for accelerator-based programming. And we are also working on high-level frameworks like Cocos. So we have a prototype there to support Cocos and also the AMD accelerators. So Scorpio is an open source product, so you can download the code. You can also contribute. It's quite portable and scalable to all major HPC systems. So we have a very large testing framework so that we can ensure that our development code runs on every major HPC system. So we started the project in 2009. When we got some funding for the German Ministry for Education and Research. We get also funding from the Department of Energy in the US. Well, as the Scorpio project started in 2009, we had some history with this measurement tools. With the older version of Scalaska, there was PRACE, and also Tau contributed to this new measurement system. So the idea was to have just one measurement system to support several analysis tools, because the measurement system is usually, from a programming perspective and a portability perspective, the most difficult part. So, and we wanted to share the effort to get the the measurement portable and scalable. And so that the measurement results, so the profiles and the traces, could then be used by several different tools. Okay, let's look at Scorpio in a different way. So here, the light green box, or the is here. This is your application. And in the process of instrumenting your application, the Scorpio instrumenter inserts these hooks here, so the dark green boxes. So this is usually done by changing your build system a little bit. So by prepending the Scorpio command to your compiler command. And what Scorpio then does is it scans the compile command line to figure out which of these hooks to insert. So for example, we have this MPI or SHMEM hooks here. This is basically a link time decision. So at link time, we look, is there some MPI in the application? And if yes, we link our own MPI library that then collects some data for MPI send, so the number of bytes sent and so on, before it calls the real MPI communication library. For thread level parallelism, especially for OpenMP, we use source-to-source instrumenter called Opari. So this was already mentioned yesterday by Samir. And so after we have this source-to-source translation, we just compile the code and link specific libraries. So for pthreads, it's similar to MPI. So it's a link time decision where we wrap the pthreads library. For accelerator-based parallelism, so it depends. So CUDA, for example, provides a kubectl library, which gets you some access to relevant data, and others just provide a specific API to or some callback API. So for I/O activity recording, so at the moment we support POSIX I/O and MPI I/O. We use library wrapping again. So here HDF5 and netcdf will be in the next Scorpio release. So and then we have the source code instrumentation here. So this in the default configuration, it is done by adding some compiler switches. So and then the compiler adds some hooks at usually function enter and function exit. So this is the default. So you get for every function enter and every function exit, you get a call. If this isn't what you want, you can switch it also off, and you can use the program database toolkit, for example, which is a source-to-source instrumenter already mentioned yesterday. Or if you want to have some either high-level phase-based instrumentation, for example, you have an initialization, you have a kernel 1, kernel 2, and some finalization. You can also add some user macros directly into your code. Orthogonal to that, we can also activate some sampling interrupts. So usually this is done while switching off the compiler-based instrumentation. So compiler-based instrumentation, depending on the compiler and on the language, can introduce quite some overhead. So for example, the Intel compilers instrument every inline function. So for C++, this can create lots of overhead. So in that case, you might switch to sampling and disable the compiler-based instrumentation. But so this here is still the standard, and we will see later in the hands-on that quite often you can come up with a reasonable low overhead. So once your application is instrumented, so it means it has some hooks, you run the application, and the hooks will then generate events into the Scorpio measurement infrastructure, into the Scorpio measurement core. There we annotate each event with a timestamp and also a location. Location is a combination of the rank and the thread ID of the current process. Depending on the configuration, we can also add some some hardware counters. So this can be configured using environment variables. So hardware counters can come from different sources. So we provide, or we support the PAPI hardware counters, but also R usage, perf, and you can also create some own plugins if you want to. If you have some specific hardware, for example, for energy measurements or some other stuff, you can create it's easy to create a plugin and to link it into the Scorpio measurement system. So, and then also dependent on the configuration, we can either write some call path profiles or some event traces. So we usually start with the call path profiles here. And the default format is the cube4 format, but we can also write directly the tau format. These call path profiles can then be analyzed using the cube GUI tool here, or tau's paraprof that was introduced yesterday. And if you have several experiments, you can also put them into a tau database to make some scaling comparisons or some other comparisons between several measurements. So usually then after you have your call path profile and you analyze your call path profile, you want to modify the measurement configuration. Yeah, so we are back here then. We add some more Scorpio environment variables and rerun the measurement, usually to create some event traces. So the event traces, as we learned yesterday, it's a chronological set of events for the different locations. Usually create a huge amount of data, which can then be analyzed either with the Vampire tool from Technical University in Dresden, or by Scalaska, which is an automatic weight state and root cause analyzer. So Scalaska in itself then creates as an output format, again, a cube file, which then can be analyzed with cube. So, so once you have this instrumented application here, you can make several measurements, either creating cube call path profiles or OTF event traces, which can then be analyzed with all the tools mentioned here. So, which is well, quite convenient. So, with just one instrumented application, you have lots of options for analysis. Okay, so Scorpio was developed or is developed mainly in Germany. So these are the partners who started the development. We also get contributions from Samir's group from the University of Oregon. Yeah, basically that's it for the partners. Let's switch to the hands-on. Now, if there are any questions in between, just ask. So let's see. No, that's not what I wanted to do. Okay. So I will keep the slides here on the right side, and I will increase the font size here in the terminal a little bit more. So if it's still too small, please let me know. So I need to connect to Archer, so please do so as well if you want to follow the hands-on. But so this here is kind of a demo, so we can in the afternoon try to do this together under your account if you want. So now I need the password for the, where is it? Two-factor authentication. Not sure. Okay, and I'm in. Okay, so what we are doing here in the hands-on is we do some program instrumentation. So we use the NASPERL benchmark, the BT MZ from yesterday. So yesterday you already did this reference run, and we will now going to modify the build system just a little bit to get Scorpio into play. Once then the BT example is instrumented, we run it in the default configuration, and then we will look at the results using Cube. So to set up, to set up the environment, we need to switch the default module, which is the Cray compiler. We are going to do all the hands-on here with the GNU compiler. So, but talking and typing frog. Okay. So on this machine here on Archer 1, we have modules, I think, for all Scorpio modules for all compilers. But just we want just to stick with the GNU compiler, which I think was the one you used for the reference execution yesterday. So we also need to do a module use to get the latest version of the Scorpio, Cube, and SCA tools. So it's a module use home, then Y07, Scalaska modules, and then we load the Scalaska module, which module loads Scalaska, which then loads the Cube module, the Scorpio module, and also the Scalaska module. So we can check this. So Scorpio should now be in pass. And it's the latest version. It's version 6.0. Okay, so it's could already see it here, and it's built with the GNU compiler. So then we go into the work directory, because we need to submit jobs from this work directory, and we go here into the project directory TA002, and in your personal directory. So for me, it's empty. So for you, you might already have the BTMZ here from yesterday. So, but I just extract it here. So, and you can find tarball in this directory. So /work/TA002 shared tutorial, and then NASPERL benchmark 3.3 and so on. We extract it here, and we then go into this directory. So, okay, so today, or like yesterday, we will build the BTMZ1. And as I said earlier, we to instrument this BT MZ benchmark, we need to modify the build system a little bit. So yesterday we looked at the config / make dev file, which is the configuration file for the or the build system's configuration file for this benchmark. So we open this file. And we will see here the compiler. So the FTN, so this is the Cray Fortran, or the Fortran compiler name on Cray systems. And as I already said, we need to prepend the compiler with the Scorpio command. And we already have this here in this file. So it is prepared for you. So we just comment this out. So we don't want this plain FDN, but we want to have this line here. So we prepend the FDN with the Scorpio command and also with the Scorpio option here. So this is the user option, which enables events from macros that were put into the in the benchmark code. So the macros are already always in the benchmark code, but only with the -- user here they are activated. So that's so basically for this application, this is the only modification we need to make in order to instrument the code. So for other codes, for other build systems, it might be more difficult. We come to this later, especially if you have a CMake application or an AutoTools-based build system. You need to take care that during the configuration step, so that Scorpio is not active during the configuration step, but only during the make step. And we have some tools and some documentation for this in another slide deck. So, but be aware, if you have a CMake-based build system or an AutoTools-based build system, this easy approach here, just prepending the compiler with Scorpio, won't work. But it's not too difficult to instrument a CMake or AutoTools-based build system. So, okay, we changed the compiler here, and this is the only change, and we added a -- user option. Then we can close this file here. There are more options to Scorpio, and you can either look them up in the online documentation, or you can do a Scorpio -- help. Here you find lots of options. Usually, Scorpio figures out what hooks it should instrument, what libraries it should link by parsing the compiler command line. So for example, if there is an OpenMP option on the command line, it will automatically activate the Opari source-to-source instrumenter. If it finds some MPI, it will link the MPI libraries. But you can, if this doesn't work out of the box, you can specify more options during this instrumentation step. Okay, so then we need to do a make clean, so to get rid of old object files. So here I don't have old object files, but if you are following the exercise, please do a make clean, and then we need to build the the benchmark again. So and if you just type make, you get the instruction here, and It's make dash mz class equals c and prox equals 8. So this is the same configuration you used yesterday. And just hit the return button and you get this output here. And yeah, here you see lots of compile steps where we just prepend the FDN compiler with scorp-user. Here is this OpenMP flag on the command line, so scorp will automatically activate the OpenMP instrumentation. And then here we have the link step, where scorp then figures out that there's some MPI in the application, links MPI libraries, also links all the other scorp libraries that are necessary for this for this benchmark. And we will find the results in the bin scorp directory. So we can just go there. Here is the output. And this is now the instrumented executable we will use for several measurements. So so the measurements, they will differ in the configuration. And as said before, the scorp measurement configuration is exclusively done using environment variables. So to get a list of all these environment variables, we have a tool called scorp-info. So scorp-info needs a command. So there are different commands. So for example, config summary shows you how Scorpio was built. But here we are interested in the config var, so which shows a list of all the measurement variables with the description that can be used to configure the measurement. So scorp-info, config vars, and here we also have another option, --full, which gives you the full description of the variables. It's not config info, it's scorp-info, of course. So, and yeah, here you see the environment variables. They all start with the scorp_. And the first two are important ones that are quite often used. So it's Scorpio-enabled profiling. This basically switches on generation of cube profiles. This is on by default. So if you just run the application, you get a profile. Then there is the Scorpio-enabled tracing, which is set to false. So if you want to do a trace experiment, you have to explicitly set this variable. So there are more variables. So Scorpio total memory, for example, is also needed, usually needed if you do a trace experiment. So to set the buffer, the internal Scorp buffer, to a reasonable size, so that you don't have to write the trace data to memory in between the measurement. So this is, you would disturb the measurement quite a lot. So you want to prevent this. And what also is a variable that is also used quite often is the Scorpio experiment directory. So to write the experiment to a directory with a reasonable name. So if you don't specify this, the directory name will be just Scorpio dash and some very long timestamp. If you have several experiments, it's in the end it might be difficult to just from the timestamp to figure out what is in there. Okay. So that's it about the configuration variables. We then need a job script, so where we specify, or where we specify the execution commands and also the Scorpio configuration. So we, like yesterday, we have a job file prepared for you. So we just copy it to our current directory. So it's in the job script Archer subdirectory, and it's called scorpio.pbs. So, and we need to copy it into our local directory. So now we have the benchmark here and also the job script. Let's look into this file and see what's in there. So the header part is basically the same as yesterday. We want to uncomment here this reservation. So I think this here is a reservation for today. Here we also unload the gray module and load the GNU module. So we specify the class, the procs, the number of threads, and we create the name of the executable based on these variables. And now we come to the Scorpio measurement configurations. Here we have just an some example configuration variables listed. So the only one we are going to use here is the experiment directory. So the directory name here, well, it contains Scorpio and then the name of the application, and then we add a _sum, so for summary measurement or profile measurement. So that's for the first experiment. For the first measurement, the only variable we are going to use. And then here in the end, we have the launch command, which is exactly what we used yesterday. So we save this file, and then we can just submit the job using the qsub commands qsub scorpio.pbs and submit. So then we wait a little bit for the output. So what we have done so far is we instrumented the NASPERL benchmark using Scorpio just by prepending Scorpio to the compile command. So instead of ftn, we now use Scorpio-user ftn. With this instrumented application, when we run it, we might specify some Scorpio configuration variables. Here in this case, we just specified the experiment directory. So let's see if there's some output here. Okay, so it's still running. So the output file is the job output is not there, but we already have this experiment directory here that we specified as a Scorpio configuration variable. So now also the output, the job output is there. We can look into the job output. And we see here what we specified in the job script. So there was a set -x. So we see the output here. And then we have this standard output from the NASPERL benchmark. We see, like yesterday, the time steps. And we also see that the verification was successful. But we also see here that the time in seconds increased significantly. So this is the runtime of the benchmark. I think yesterday it was around 20 seconds. Now it's 40 seconds, so time doubled. So this is not so good. I think we need to investigate this further, which we will do in a later session. But so the run was successful. It took it took a little longer, or it took twice as long, and it generated this Scorpio BT and that some output directory. So let's look what's in this output directory here. So there are 3 files. So there's a manifest file, so which is basically a file specifying what we would expect in this directory here. So we would expect a Scorpio config file. So this we will look at this later. So that lists all of the environment variables that were used for this run. So if you want to redo this run, or yeah, if some time passed once while you had done this run and you can't figure out which script you used, you can look at this Scorpio config file here, and you can specify all the environment variables so that you can redo the experiment. And then we created the profile, the output format in the profile output measurement in Cube4 format. This is the real measurement output that we are going to analyze with the Cube tool later. And then here, in the end, we get a complete list of Scorpio environment variables that were used, so and explicitly set for this measurement. So the only one which was explicitly set was the environment variable, the experiment directory, and everything else was kept as default. So let's look at the list of the Scorpio configuration variables. So this is just a list of all the variables. So we see here that we did a profiling experiment, tracing was off, and all the other stuff except the experiment directory was used with the default values. Okay, so now we can look at this profile.cubex file. We usually do this by calling the cube GUI tool and passing it the profile.cubex. I think I didn't log into Archer using X, so yeah. But we will look at this in the session, and I hand now over to Brian to tell you a little bit about the cube tool in general, and then to look at this profile.cubex experiment. So well, quite often it's using cube via an X connection is quite slow, and you might or it's quite often it's easier if you copy the profile.cubex file to your local workstation, and then use a local cube there. So I think I have some experiments here. So just to see how it looks like, I just open it, but explanation will then come from Brian. So here is how it should look like. But now I hand over to Brian, if there are any questions, so feel free to ask now or later. Okay, Brian, then I stop sharing now.
Yes, I'm starting to share my slides.
Okay.
Click on them. Okay, so I'm just going to show you a few slides of introduction, and then we'll move on and actually look at an interactive session with Cube. So I'm Brian Wiley from Jülich Supercomputing Center, work with Christian on the development of these tools. You already saw a picture of Cube. The name Cube comes from this idea of having 3 dimensions of data that we can explore, and Cube is the tool that we use for exploring the profile and trace analysis data that is collected with Scorpio and written by Scalaska and other tools. As well as the GUI for doing this analysis, there's additional utilities which we might cover that allow you to do some additional processing to combine different measurements or to do differences between them. There's a number of what we call algebra utilities that allow you to do those sorts of operations. Historically, Cube was developed as part of a predecessor to Scalaska and then developed further as part of the Scalaska toolset, and now used with Scorpio and with Tau and with other measurements as well. It's a separate component that can be installed separately, and it typically makes sense to install it on your laptop or your workstation rather than run it remotely. That's what I'm going to do in a moment. That's what I recommend that you also do. Go to the scalaska.org website, and then you'll find an area for software downloads. You want the one for the Cube 4X, the latest version of Cube, and then there's packages there for Windows, Mac OS, or Linux packages that you can build and install on your workstation itself, on your laptop itself. The installation on Archer is available. You can run it there as Cube, as Christian mentioned. You need to make sure that you have X forwarding set up to do that. That can either be done with SSH-X, or if you're using PuTTY or some other infrastructure, you may need Xming or something else to provide the X server. But those are alternatives to be able to look at these and explore these graphical tools. The way in which it will look will depend on your environment and the configuration. So the decorations and the fonts will differ, but of course, the other thing that would change will be the data and the measurements that you have itself, the times. So as I mentioned, Cube is based on this notion of having 3 dimensions of data. We have information about different performance properties, performance metrics. That can be considered one of these axes. Orthogonal to that, we have the different call paths of execution. We can consider those to be a hierarchy as well. And then in the 3rd dimension, we have what we call system locations. These are the compute nodes, the processes, the threads, which are the underlying units where measurements are taken. In the Cube display, we're able to see the metrics for each call path, for each location, presented in different ways. They're presented as numeric values if you need a lot of detail about precise numbers. But when you're trying to navigate substantial amounts of data, that can be quite challenging to look at screens and screens of numbers. So that we provide a color coding, which helps us to be able to easily identify the highest values, the lowest values, the extreme values, and those are typically the ones which are most relevant and most interesting to focus on. By using the hierarchical nature of the data, we can navigate through the tree, we can expand and close nodes, and the values will change which are being presented depending on whether the node we're looking at is a closed node, when it will show the inclusive value of everything contained within it, or if it's an open node, an expanded node, we will see the exclusive value, the value just for that call path itself without anything that's called from it. And there's lots of customization that's possible to show things as percentages, in different ways. We'll see a few of those, but you can also explore these at your leisure. These were the three dimensions that I was referring to. On the left-hand side, we have different performance metrics, which we can look at, and there may be hierarchies here that we can expand. The application executes, and from that execution, we get a detailed execution call tree. We see the different call paths of execution, which we can focus on. That gives us context information about what the metric refers to for a particular routine, a particular call path. And on the right-hand side, we have the different locations, which processes and threads were collected in this measurement, which compute nodes they were running on, and we'll see how these values relate to each other in the demo session, which I'll come to in a moment. This slide here for orientation is one you've seen a couple of times, showing the relationship between inclusive and exclusive values, whether we're looking for values for the entire function foo in this case is the yellow or green part here, as opposed to the exclusive part that's only in foo that isn't related to anything called from foo, such as this call path to bar here. That would be the red part in this case. So by using the call tree and by expanding and closing nodes, we can actually present a lot of metric information in a relatively concise form, a very dense form, which allows us to navigate through it. At this point, I'm going to switch to the demo session. The slides you can follow if you wish. They are basically going to just take you through things and show you step by step what I'm going to look at in the demo. So let me switch to the demo, which I have. Okay, so it took a few seconds, but this is it's not exactly the same measurement that Christian just collected. It's the one that I collected previously to that. And as I said, I've copied it to my workstation here, my laptop here, so that we can actually interact with it a little bit more conveniently. Remote interaction through X can be a bit sluggish at times, so it's a little bit more convenient to have things locally, which is what I have here. As I said, we have metrics on the left-hand side. We'll look at those in a little bit of detail later, but at the moment I have the metric selected for time. This isn't the execution time, the wall clock time. This is the aggregate time. This is a CPU time, the time that you will be charged for the use or for the execution of this application. And so that's the aggregate time for all of the processes and threads, which we can see on the right-hand panel here. So at the top, we're seeing again everything aggregated, but if I click on the expander here, I can see that we actually executed things on 2 compute nodes, 36 and 37. If I expand those nodes, I can see the different processes that were executed. We had a configuration for 8 MPI processes, so those are the 8 processes that I'm now seeing here. And on each of those processes, we actually had 6 OpenMP threads. And so if I expand the tree further down, this is where I see the OpenMP threads that were running in each of those MPI processes. So our execution time was around 40 seconds, and that's why we're now seeing that each of the threads, at least each of the master threads here, was running for a little bit more than 40 seconds. And when we aggregate all these numbers together, the values for each of the threads, these numbers, when they're aggregated here, come to a total value of 235 compute seconds, and that 235 is the value that I see when the node is collapsed here, and when it's open, in this case, there's no time for the MPI process itself, which isn't attributable to one of the threads inside it, particularly the master thread, which executes from beginning to end. The OpenMP threads, they're only executed within the parallel regions, so that's why they have a little bit of less execution time than the master threads itself. And when I aggregate the value from the 4 processes here, then I get the value for the compute node. And when I aggregate the value of the 2 compute nodes, I get the value which is shown in the panels to the left-hand side. And ultimately on the far right, I see the total compute time, CPU seconds, was in this case 1800 seconds, 1880. So what I select on the left determines which metric I'm looking at here. If I switch to another metric, the values to the right will change according to that metric. If I look at the number of bytes which are sent and received, I can see again that how much data is sent by each MPI process, and I can see that it varies across the processes. I can also see that the message passing is actually only done by the master thread in each case. This corresponds to the MPI thread funneled execution model for hybrid execution. If I had MPI operations done by other threads, I would see those here, and that would correspond to one of the other MPI thread execution models. But since time is money, time is what we're typically charged for, I'll go back and look at that in more detail. And we would like to see what we would see in a normal execution profile, how that time is broken down by execution call path. When I expand the base node here, I see what would be considered the main of a C or C++ application. It's the name of the program for Fortran code here. When I expand that further, I see the different things which were done inside the program itself. There's some initialization which is done at the beginning, the MPI init thread executed by the master processes at the very beginning. There's also some creation of communicators and splitting communicators. All of this is part of the setup for the benchmark itself here. Likewise, we see an MPI finalize, which is executed at the very end. So those init and finalize are the sorts of things you'd expect to see in every MPI application. If the application doesn't finalize, if it crashes in some way, the profile would be incomplete and actually won't be generated. So you have to make sure that the application runs successfully to completion, executes MPI finalize, and at that point we would be collecting together the profiles from each of the processes, each of the threads in those processes, and collating them into what is now shown here as our profile.cubex, which has everything automatically integrated together. Most of the time is actually not in those calls, which is what we would expect. By using the color coding that we're seeing here, most of the time is actually in this part which is shown here as iteration. If I expand that, we see there's an exchange of boundary conditions, and then there's also an ADI solver here. Inside the ADI solver, we see there's something computing the right-hand side. We can see that there's different solvers for X, Y, and Z directions, and that's actually where most of the computation is done in this case. But what's interesting is that inside these routines, if I expand them further, we'll see that's where there's an OpenMP parallel section. So the outer part here, such as the ADI, that's only executed on the master thread. That's outside of the parallel region. When I select the xsolve itself, I'm seeing that there's some compute time for all of the threads here. And if we see inside that, we'll see that there's an OpenMP parallel do loop, and that's explaining what we're seeing executed on the OpenMP threads in this case. And we can see that execution on the different MPI processes. Inside that do loop, we also see the different computational routines which are executed inside it. And if we select those, we'll see the compute time for those as well. So there's a number of routines here that are executed inside the OpenMP do loop. At the end of the do loop, there's an implicit barrier synchronization that's marked here at the end. And what we see here is that the time in that barrier is actually varying quite a lot across the OpenMP threads. Some of them spend very little time in that barrier, others spend a little bit more. And that's an indication that there was some imbalance in the computational do loop here itself. So if I was actually to aggregate the time for within that do loop, that had some variation. We saw that some of the processes, some of the threads took longer than the others. and the ones which were faster then actually have larger amounts of time in the barrier at the end. If I select the barrier as well, we then see that everything is much more balanced. So the barrier is catching and presenting the imbalance of the execution time of the different OpenMP threads itself. So just to briefly show things in a little bit of different way, instead of showing the execution times here, I could switch and show things as a percentage. Different ways. I'll take the percentage of the metric that I've selected here, and so instead of seeing timing values, now I'm looking at the percentage times. I see that 6%, 6.2% was actually executed in this routine, 2.9, 4.1% in those ones. Likewise, on the right-hand side, I could also show different percentage modes here. The percentage of the selected metric, in which case I see that there's roughly 1% executed, sorry, 0.1% of the total execution time for this routine. If I back up a little bit, the numbers are a little bit higher. If I look at the xsolve itself, again, we're seeing the variation of those times across the threads. Since there's typically lots of threads executing, I could expand them all, and then I have to do a lot of scrolling to see where those values are. Even if I present to a peer percentage mode, the peer percentage is taking the highest value and then showing the other values as a percentage of that for the other threads. That shows me that things are relatively balanced here when looking at the xsolve, for the y-solve, for the z-solve. Here the load balance is a little bit more varied, and if I was to go in a little bit further or look at the just the barrier at the end, we see at a glance there's much more of a variation here. So again, here some of the threads are taking much longer waiting in this barrier at the end of the execution, and the higher values here with red or orange colors are much higher than the ones which are on this color scale at the bottom, where we're seeing blues and cyans, very light colors here. But since there's lots of threads and processes here, again, we need a little bit more of an overview than that. That's why there's a couple of other presentations we can look at. This statistical presentation is showing the range of values from the very lowest value to the very highest value, and again, showing things as a percentage here. So we see some of them have very low waiting times in this barrier, others spend a bit longer. If I look at the violin representation, I get a more detailed presentation of that variation. But if I go to the topological view, here we're looking at a matrix of processes and threads. The processes are the 8 processes in the horizontal dimension here, as shown by the legend at the bottom. The threads are what we're seeing in the vertical in this case. So the master threads have very low values on each of the threads. That's why they're shown in the dark blue color here. If we look at the values for the other threads, those are a little bit higher. The one here at the very end, this is on the highest process and the highest thread on that process. That's the one that has the darkest color, the reddest color here, and that's why it has the highest value in this presentation here. So that's the one that had the least amount of work and therefore the corresponding largest amount of waiting time. So we can see at a glance here how things vary across quite a large collection of processes and threads, and we'll be able to exploit that in future analyses. Just to compare the X and the Y solve, they don't have quite as much imbalance as, or they have a different pattern of imbalance here. So when we look at what's happening in the X and Y solve directions here, we see that, again, there's an imbalance. We see that the master thread and the first thread in each case, they have less waiting time. That's an indication that those threads, those processes have a little bit more work than the others. That's because when the work is partitioned, when it's allocated to threads, in this case, it's not possible to allocate it equally. The problem doesn't split equally into 48 in this case. and that means that there's always one or two threads that have a little bit more work. They spend longer in the computation, and therefore, because they take longer they have less waiting time at the end. Likewise, in the Y direction and in the Z direction, things are even more challenging. There, it's even more challenging to balance things, and we're seeing an indication of that in the range of colors, which I believe you can see here. And when we look at the imbalance at the end, we see there's more of an imbalance there as well. Part of that imbalance we could explain in terms of how often this computation is done. So if I look at the physics metric, which we're seeing on the left-hand side here, if I go in this case here first, here we're seeing how often these routines are executed. Previously, we were looking at how long they took, but what we're seeing is that how long they took is directly correlated with how frequently they're actually executed. And we're seeing a different number of calls, different numbers of executions across the processes and threads. If I wanted to see the actual numbers, I can click on them, and on a right click, it brings up a dialog that's showing the value. As a percentage, it's perhaps not so indicative, but if I go back and look at things as absolute values, we're seeing that the number of times that they're executed is varying across the threads as well. And so that's one measure of the fact that there's imbalance coming from the number of times that these routines are executed. In the Z case, we see, again, they're not executed even the same number of times, distinguishing thread 1 from thread 2. The higher numbered threads here have fewer calls to these routines, and that again is related to the fact that they end up taking longer when they have more work to do. We'll also see that these numbers are relatively high, and that's perhaps a concern for us because the number of times that they're executed can be a factor in how much data we would collect for them, especially when it comes to the trace collection and the trace analysis. So where these numbers of visits to different call paths start becoming high, those are perhaps routines that we want to be concerned about and think about perhaps filtering out of the measurement. Whereas routines which give us context, which tell us about the things at the OpenMP and MPI level, are typically the ones that are most relevant for our analysis, for looking at the communication and synchronization times. Those are the ones which we would be most interested in keeping. If I was to try and find out where MPI is done in this application, it's not inside the parallel regions here. It's actually outside here in the, actually not even in there, it's in this exchange. That's where we are seeing the MPI calls. In this case, we're seeing non-blocking sends and receives, which are done. They're done by the master threads outside of the parallel loops. For every MPI send, we see there's a corresponding MPI receive and an MPI wait all in this case, which is actually matching or completing both the sends and receives. So that's why the number of wait all calls is again 1400. It's the same number as the sends and receives. If we were just to do a wait for each of them, then that number would be twice as high. More interesting than the number of visits is the time in those. In this case, we see relatively small amounts of time in the non-blocking send and receive. Most of the time is actually in the wait all operation, and then we're again seeing how that varies across the processes and threads in this case. If I close everything down so we can see everything, we're seeing that there is some variation across the different processes here. That's an indication that there's some imbalance that's already starting to show up, and that we're seeing that even with only MPI processes here. But we can see how it compares across the different compute nodes. And if we were to execute this with more MPI ranks or on a larger number of MPI compute nodes on Archer, then we could see how that communication time varies. So those are things that we can look at later, or you can look at later. We're not going to look at that here. But as I said, there's also additional metrics here for the amount of data that is sent between processes, the data sent in the MPI send operations. We see that again that is varying across the different MPI ranks and the MPI received. There's no MPI data received in the non-blocking receive itself. All of the data is actually received in the corresponding wait all operation that comes at the end. And as a consistency check, we might want to compare the amount of data that's sent and received. In this case, it has to match, and it's matching exactly. We're seeing that there's communication done in the exchange here. Within the iteration region that's marked here, the other place where data is exchanged is in a warm-up iteration, which is not part of the computation that's timed for this benchmark, but we're seeing that this exchange and this ADI, those are actually executed. There's one execution which is done outside of the benchmark routine or the benchmark region. Those are, of course, timed separately. If we didn't distinguish them, as in this case, we've marked the iteration for the benchmark routine explicitly. That allows us to distinguish what's happening in the benchmark from what was happening in the warm-up. That was one of the cases where this explicit annotation of the iteration has some value. You may want to do some other annotations. You may want to distinguish different solvers that are not distinguishable by the name of the routine itself. It may be that you want to explicitly mark the initialization and distinguish that from a solver. There are lots of ways you can put in these annotations and have them marked, and then be able to exploit them in the analysis which follows, whether it's a profile analysis, which we're seeing here, or trace collection and trace analysis, which we'll come on to in a few moments. The other special region that's been marked here is one where measurement was explicitly disabled. This was part of the initialization, which was again not interesting for us, so we explicitly marked it with macros which said we would disable measurement for that period, and that's why it's shown as a period where we don't have anything other than the time and how often it was executed here. So executed once by each of the master ranks. We see the time in it, but we don't see any additional details. We don't see how much data was transferred or additional call paths that were executed inside that explicitly disabled measurement region. But for everything else, we have a lot of detail down to very detailed levels within the parallel regions and for each of the MPI operations which are done. And those are the sorts of things that we would be more interested in looking at in more detail. We'll see those in more detail, but our first challenge, our first step, is to try and understand why this measurement took twice as long as the reference measurement without instrumentation. And so there are various things that we can do to do some initial analysis of this measurement and refine it and refine the measurement configuration, refine the instrumentation so that we can reduce the measurement overheads and just collect the information that we would be really interested in for further analysis. So I think that is enough for now in terms of just looking at this initial measurement. It shows the basics of what's included in the measurement, and we'll come back and look at a more realistic, a more refined measurement a little bit later. But Christian, if you're ready, I think we can go back and continue. I think we have, if there are questions, we can take those, or we can continue with perhaps the first part of your next presentation.
Okay, so we have 13 minutes left until the scheduled break, I think. But yeah, I can continue with the filtering now. So I will share my screen. Okay, so let's see. Okay. So we made our first measurement and collected a profile. Brian showed you how to analyze it using the cube tool. And we looked at the call path profile, investigated the time metric and the visit counts and the MPI message statistics and more. But the question is, how good was the measurement? So we got the desired result, but so the execution took twice as long as the reference run. So we need to dig into what's causing this large overhead. So therefore, in this session, we do summary experiment scoring. So this basically means we look into the profile measurement and see what kind of regions, what kind of functions contribute to the time, to the visits of the experiment, and then we try to create a filter to filter out stuff that's causing a large overhead and that's potentially not necessary for a subsequent trace measurement. Okay, sorry, wrong direction. So I think we can then switch back here to the terminal. So we are still here in this bin Scorpio directory where I did the Scorpio measurement. The result here is in the Scorpio BTMZ sum directory. And we are now going to use a tool called Scorpio Score. It's a command line tool to look at the generated profile measurement. So we just pass the Scorpio Score the profile.cubex file and get some high-level output here. So first line is telling you that if you would do a trace measurement, so this basically means Scorpio enable tracing, so you need to set this environment variable. So if you just set this environment variable, you would generate traces that are 159 gigabytes of size, which is quite a lot. And so for each rank, it would generate 20 gigabytes, which is way too much. So because the Scorpio total memory per process, so per rank, is just 4 gigabytes. So just doing a trace measurement as is would not, or it would work, but it would write during the measurement trace buffers to memory 5 times. So 5 times 4 is 20, and this would disturb the measurement quite a lot. So we don't want to do this. What we also see here is what kind of functions contribute to the trace buffer requirements here, and also to the visits, the time and time and percent, and also time per visits. So the different types we see here, these are user functions, so which contribute the most amount to the trace buffer requirements here, and also to the visits, but they have a very little time per visit. So these seems to be small functions that are executed a huge amount of times. So these might be candidates where the relative overhead of measurement is quite high. So because if we measure or the time Scorpio needs per event, so to collect timestamp, to collect some other data, is relatively constant. And if the execution time of the function is quite small, the relative overhead is quite large. So then we also have the the OpenMP functions here. Then the MPI functions, which is also straightforward. And then we have these COM functions here. So these are combined functions. So this might be user functions, OpenMP functions, or MPI functions that then call some other functions. You can see this here in this diagram. So the leaves here are either user functions, OpenMP, MPI functions, and in between you have something combined. And so the idea for this categorization is that if you're going to do some trace measurements that are targeted towards finding communication weight states or communication root causes, so then you're mostly interested in this OpenMP and MPI functions here, but you're not so much interested in this user regions that don't contribute to communication call paths. Okay, so again here we have a huge amount of memory, 20 gigabytes per rank, and we need to do something about this. So if we want to dig a little bit deeper into this Scorpio score output here, we can add the flag -r for regions. So if you use this flag, then you, in addition to this high-level output here, you get a breakdown per region. So let's do this. Okay, I need to increase here size a little bit. So here is again the this header we saw before, and from here on we see the contributions of the individual functions. So here this matweg sub, matmul sub, and so on. And these are sorted by the trace buffer requirements here. So this max buff. So if you want to measure this matweg sub in a trace experiment, you would need to reserve this amount of memory in Scorpio. And but this is a pure user function. So basically all the first 6 functions here are pure user functions that don't contribute to this COM or OpenMP or MPI functions here. So these are candidates for filtering. So this doesn't mean that these functions don't need some tuning or some further analysis, but for doing a weight state analysis using Scalaska, these functions are not so relevant here. So you still can analyze these functions using some performance counters, so to see if there's something wrong with the cache usage, for example. But this is not the strength of this Scalaska tool, which will concentrate on the MPI, on the communication analysis. So, okay, here, yeah, we just see if we add up this this first 6 numbers here, then we see that this is roughly 20 gigabytes of memory just for these user functions that we think that we might want to get rid of. So as a summary, so the total size of an event trace would be nearly 160 gigabytes, which means 20 gigabytes per rank. And so nearly 100% of the trace requirements is in the user region. So these are purely computational regions, so that will not contribute to any OpenMP MPI communication analysis. And they also contribute 41.5% of the total runtime. So this can be seen here if we no. So here is this 41.6 here in my experiment. This is the time for the user regions. But as I said, the time per visit is very small, so the relative overhead is quite high. So so it's quite likely that these functions are a big contributor to the double of runtime we saw in the experiment. So we are now going to to get rid of these functions in the measurement. So without recompilation, just by specifying a filter file and adding one Scorpio environment variable to the job script. So what is a filtering file? So we have a prepared filtering file here. So let's look at it. It's in config or pfilled. So it's a text file, and where you see some keywords here. So this is Scorpio region names begin and Scorpio region names end. Between these keywords, you can see you can see here an exclude keyword. There's also an include keyword. So, but here we want to exclude this user regions that don't contribute to the COM user regions. So so these are the 6 regions we saw in the Scorpio score output, and there's in addition this timer underscore. So you also see here this asterisk. Here, this is because function names, depending on the compiler, are mangled. So the Fortran compiler, the GNU Fortran compiler, sees this function here with an additional underscore, and to get these filter files portable, you can use some wildcards here. So with this filtering file, we would record every compiler instrumented regions except the ones listed here. You can also do an exclude star, for example, and then include just a few functions. So there are different ways of writing a Scorpio filter file, but for just excluding user functions that contribute lots to the overhead, this would be the easiest way here. So we can also do a somehow simulation of how this would affect the next experiment. So we do again this Scorpio command, but now we pass this filtering file in addition to the profile. Scorpio some profile dot cubex. Oh, interesting. Well, again, Scorpio score dash f. config Scorpio Feld Scorpio btm some profile.cubex. Okay. So now we are doing the scoring again, but we apply the filter file. So we see here the unfiltered result as before, and here now we see the situation after filtering. So we see here that this amount of functions or this amount of buffer space is filtered out, so we don't need it. This means this amount of visits we will not see. And overall, the estimated size of the trace file was reduced from, I think, 159 gigabytes to 659 megabytes. And the maximum amount per rank is now 83 megabytes instead of 20 gigabytes. So, and with the environment variable set to Scorpio total memory equals 59 megabytes, we could do a measurement without intermediate trace flushes. So, okay, so if we are going to also include some performance counters, for example, we can also use Scorpio score to estimate the trace buffer size here. Need to just add -c and the number of the counters. So you just do the -f for the filter. And now, if your next measurement would be with, for example, 2 PAPI hardware counters, you add a -c 2, and then specify the profile. And you see here that adding 2 hardware counters per event increases the Scorpio total memory, which is required from 95 to 250 megabytes. So with this tool, you can prepare your next measurements. And so as we are going towards a trace measurement today, we filter out all these user regions and just keep the OpenMP and MPI stuff, and also the combined regions here that then lead to the MPI and OpenMP leaf nodes. Okay, we can also do a or look at the Scorpio score output breakdown with the regions, with the filtered regions. Let's do this quickly here. And here again, we have the header, which is not changed, but here with the plus sign, we see all the functions that were filtered out. So here the first 6 are filtered out. Then we have the usual OpenMP ones. And in the end, I think we also see some user regions here with the timer stuff that we also put into the filter file. So how would a filter file be activated? So this is again done using an environment variable. So we look again into the job script. Here in the first experiment, we just set the environment variable. So we don't want to, as we are going to do a new experiment, we just use a new experiment directory name, just add a filter here. And we need to activate the Scorpio filter file just by exporting the Scorpio filtering file environment variable that points to these to the text file we just saw. And with this slight modifications, we can do the next Scorpio run. So we are still working on the old executable, on the instrumented executable. As said before, you usually instrument once, and then you can do lots of measurements with different configurations, where the configurations are done using environment variables. So just submit this. And okay, here, this in the slides, you find this as reference. While this is running, we can briefly look into different filtering options here. I already told you about the Scorpio region names begin and region names end. So these are the two keywords with this exclude here, and then you list the name of functions, and you activate this file, or you apply the filter using the Scorpio filtering file. There is also an option to use this filtering file for compile time filtering, which reduces the overhead even more. But this would mean recompilation. So, and this works just for the GCC compiler right now. We are working also to apply this for the Intel compiler, but this is not released yet. But as we will see later, using this runtime filtering here, so working on the old executable, it reduces the overhead by quite a lot. So there are two top-level keywords here. So you can filter by file names here and have an exclude and include here, or you can do it by region names as we did so far. So all this exclude and include here between this begin and end are evaluated in sequential order. And the regions that are excluded after all rules are evaluated then get filtered. So, and you can use this bash-like wildcards here, this asterisk, the question mark, and also you can the square brackets. Here's the same for the region names, yeah, which is basically the same, just that you filter for region names and not for file names. Then there's also the name mangling. So as I mentioned before, the Fortran compiler usually adds an underscore to the function name. So at least this is then seen in the object files or by tools like nm. We need to take care of this dependent on the compiler. So, but if you want to create a filter file, a good starting point is the output of Scorpio score. It gets a little bit more tricky if you have C++ codes and overloading. Here is a little example. So how you would filter a function that Scorpio score displays as void bar and an int parameter, in star parameter here, and you can use then the question mark here to fill in the blanks, for example. But you can always use the Scorpio score with the -f option to see if your filter applies correctly. Okay, so meanwhile, I think the execution should be done. Okay, here we see the output directory and the the output file. Let's have a brief look before the break into this file. So we see the benchmark output as before, and we are now interested in the time per second. So is the time got reduced, so the overhead is, or the execution time is close to the execution time of the reference execution, which is it's a very good result. And we also have we also look briefly at the contents of the new experiment directory. So in addition to the 3 files we saw before here, we have the Scorpio filter file, which gets copied in the experiment directory. So if you want to rerun your experiment, the filter is there for later reference. So we could use Cube again to look at this profile.cubex, but I think we are now going to have a break, and after the break, I think we will continue with Scalaska, maybe, and after that, or Brian, what do you think? Shall we do the Scalaska first, or?
We'll continue with Scalaska after the break, but we should extend the break to be 30 minutes. So we'll be starting at 1/4 the hour, if that's okay.
Yeah, for me it's okay. Yeah.
Yeah. So we take a 30-minute break now. We restart at 1/4 the hour, and if you have questions, put them into the chat. I'm actually going to grab some lunch, but I'll check those when I get back. Christian, maybe we'll check them in the interim. If you have any questions about what we've covered so far, or you're trying to install Cube, we can try and get that done during the break or over lunch when we get to that part. So we'll see you in 30 minutes. So by my watch, it's now 1/4, so I think we're ready to continue. So in this next session, I'm going to be presenting the Scalaska tools for trace analysis and trace collection. And we'll be using Scorpio as we saw earlier this morning. And you'll have a chance to see how the additional trace information is incorporated into the profiles presented by Cube. We saw on Tuesday, yesterday, that in the traces that were collected by X-ray, there's lots of very detailed information that's possible to be collected about message passing operations or synchronizations between threads and processes. And searching for patterns of inefficient behavior in this can be quite challenging. It can be done interactively, of course, but the idea behind the Scalaska tools is that we would like to automate this process and provide an automated way of going through the entire trace, where we're guaranteed to cover everything, to find the most significant inefficiencies. We want to classify the execution behavior, quantify the significance of the interactions between processes and threads, and take that further. We can also identify where there are delays and where there are root causes that are underlying these inefficiencies. So the picture that you're seeing here is an attempt to show how, after collecting very large amounts of event trace data, and this can be many gigabytes, many terabytes in size, especially if we're dealing with very large numbers of processes and threads, we can then distill this down in an automated analysis into something which is much more compact, easier to review, and very similar to the profiles that we just saw this morning in this three-dimensional space, where we still have information about each of the execution call paths, which processes and threads they were executed on, but we can augment the property dimension by adding additional metrics which can give us more insight into these sorts of inefficiencies. Doing this in a serial form, just trying to go through the entire trace, is a real challenge because the amount of data is very large and becomes quickly unmanageable. So we exploit a parallel replay analysis, which means that we would analyze the trace with the same resources as were used for its collection. If you're collecting a trace on 10 compute nodes with 100 processes, we would use exactly those same 10 nodes and the same 100 processes to analyze the performance by replaying the trace, sending events between the different processes that are captured from that trace, and by analyzing those, figuring out when they were sent and received, we can do this in a very scalable form, so that the trace analysis, the parallel trace analysis, typically is taking about the same amount of time as the trace collection. Depends what's included in the trace, of course. It can be much faster in many cases. In some cases, it might be slower if it's a very communication-intensive trace. But you should expect it to be roughly the same order of magnitude, at least as a starting estimate. Of course, the analysis can be done on different resources, but if you're analyzing with fewer resources, the analysis can take correspondingly longer. So that was our objective when we set out to develop Scalaska. This was a follow-on to a preceding project which did the trace analysis in a non-scalable fashion that was quickly a bottleneck. But by doing it with Scalaska, we targeted the most common, the most popular programming paradigms. Of course, this is MPI for message passing and OpenMP or POSIX threads for threading. So we don't have the ability to analyze events from GPUs yet or from other programming paradigms. These are things that we might want to incorporate in future versions. But with MPI and with threading combined, we're covering the most popular programming paradigms currently. And we were challenged to be able to do this analysis on some of the very large-scale systems, the Blue Gene systems that we had here in Jülich with up to 1 million and more cores in them, or the largest Cray systems, the K computer, and other very large systems with very many processes and threads, which we needed to be able to collect the traces with Scorpio, for example, but also to analyze those traces in a scalable parallel fashion. So that scalability was built in from the start and has allowed us to be able to do trace analysis of very large traces of terabytes in size in some cases on these very large parallel systems. Typically, Scalaska releases are coordinated with Scorpio. We didn't do a release with the latest Scorpio release because the current version of Scalaska is able to analyze those latest traces as well. It's using the same OTF library and the other libraries underneath. It's open source, like Scorpio, with the 3-clause BSD open source license, portable to the same systems as Scorpio, and it complements what Scorpio is able to provide in terms of instrumentation and measurement capabilities. We already saw the cube presentation and analysis capabilities, which we're exploiting as well. So those are components which are exploited and used by the Scalaska toolset. As I mentioned, we're not able to analyze all of the traces that are collected by Scorpio, but we're able to handle a large proportion of them, and those are the ones that we'll focus on in the course of the exercise later this morning. So this diagram here is an attempt to show how Scorpio and Scalaska fit together. We've already seen how Scorpio takes the source modules, the source code, works with the compiler and linker to make sure that those are instrumented and the Scorpio libraries for measurement are linked in with the executable. So we end up with an instrumented executable that can be then used for subsequent measurements. When that executable is launched and run as multiple processes, we have all of the instrumentation enabled within that executable. We can configure it at runtime, saying what we're going to collect, whether this is additional hardware counters or additional things we're going to use in the measurement. And as a first step, we would be doing a summary measurement where we've collected information from each of the processes and threads in memory during execution into internal profiles. Those then get collated together and merged into a single summary report, which can be post-processed and analyzed in various ways, as well as being interactively explored and analyzed with the Cube GUI. That's what we covered already this morning. We already went a little bit further this morning by saying how we can do some cross-processing of this initial measurement to do some determination of how we might want to optimize and improve the measurement configuration by filtering out certain things, potentially by adding other things that we'd like to see in the measurement, additional routines, additional hardware counters, for example. So there's an iterative process here at the top where we can go through a series of summary measurements, additional filtering to remove things, additional measurement configuration to add things, and at each stage we can review that measurement and see what it contains and see if there's things that we would like to add. But one of the key things that we can do is we can do a runtime configuration to enable tracing. Setting the environment variable or flicking a switch allows us to collect event traces in memory. Each process and thread will then be collecting a time-stamped set of events in memory, and at the end of execution we would write those to the event trace files. So that's what we'll see in a moment, that we have a trace file collected from every thread and every process, and then those are the traces that we would actually be analyzing with the Scalaska trace analysis. Again, that's done in parallel with the same number of processes as used for the initial measurement, and that allows us to do it in a parallel fashion. But at the end of that, we again get an augmented profile from every process and thread that we can collate, combine together into a weight state report, which again is in a similar form, a cube format, that allows us to show that and explore that in the cube analysis display. The key thing to note is that the part which is highlighted with the orange background here is the part that's happening as part of the trace analysis. It's happening in parallel on the compute node. So we want to run this as part of the job where we're doing the measurement itself. It can be done separately if necessary, but it's most convenient if we actually just combine it with the measurement itself, and we can just analyze the traces immediately after they're collected and distill things down into a more convenient form for presentation and for exploration. So that's what we'll see in the course of the next hour. The sorts of things that we're looking for in this trace analysis are things like weight states, where if we consider what's happening on each process, this diagram is showing what might be happening when we have two processes, maybe two of many processes. We see that some of them are doing send operations, some of them are doing receive operations, and if the corresponding message that is being sent is sent in time, then the receive process will have to block until the corresponding send is at least initiated. We don't really know what's happening inside the MPI library, so we don't know if that send is sent at the very beginning when the dotted line is here, or whether it happens a little bit later. There may be some rendezvous going on, there may be anything going on inside MPI, but we know that the send certainly won't be started until the MPI send is initiated on in this case, the sender process. So this dark, large double-sided arrow here on the second line is indicating a wait state on the second process, where from when it entered the MPI receive, it had to wait at least until the point when the corresponding send was initiated on that process. If we consider the non-blocking scenarios, the one on the right here, it may be a non-blocking receive, which is fine. The process can then do some other work in the interim, but as soon as the process reaches the MPI wait operation for that request, it will have to block in the same way until the corresponding send is initiated. Again, if the send was initiated before the MPI wait, there'll be no waiting time, but if it's initiated afterwards, at least the time up until the send is initiated can be considered waiting time, and that's what we would report as such in the Scalaska tool. It may be that the send is a non-blocking send, in which case the message would be initiated and would be transferred, but again, it won't be initiated until the MPI send is initiated, so there's a little bit less waiting time in that case. Or it may be that both sender and receiver are both non-blocking, and we have to deal with that case as well. So in each case, there's a point-to-point communication that's going on, and the receipt of that message can't actually be initiated until the corresponding send has been posted. And those are the sorts of patterns of interaction between processes. It's one example of what we would be looking for in the Scorpio trace analysis. What you're seeing here for point-to-point communication, we would also do similar analysis for collective communication. If there's a barrier, none of the processes can continue past the barrier until the last one has reached it. And so there'd be waiting time on all of those other processes until the last one reaches the barrier. If it's another collective operation with a reduction, a gather, an all reduce, then there are different patterns, there are different processes involved. Often one of them would be the root process, which determines which one the others have to wait for. We would identify that. The ones which start the operation before the root are ones that would have waiting time. The ones which happen after the root potentially don't have waiting time. So the trace analysis replays the events, goes through the events in the trace. It is not replaying the actual send itself in terms of the data that was sent, but it's sending the timestamp so that when we are on the receiving process, we get the time of the corresponding send operation when it was initiated. And then that time is what we would process to subtract from the time of the initiation of the wait or the initiation of the receive as the waiting time for that process, if that's the one that has waiting time. If it turns out that the send was initiated before the receive, there's no waiting to be attributed in that case. So there's a lot of complex interaction there that allows us to go through the entire trace, and by aggregating this information for all of the events across all of the processes and threads, we can get an overview of the patterns of inefficiencies. Going beyond that, we can actually figure out what is the critical execution call path. There is one path through the events in the trace that determines the execution, and that's what's been highlighted with the darker color in the background here, this red color in the background. In this case, the critical path of execution started at the bottom, it transferred to the top, and then it was ended on the process in the middle. Typically, there'd be many more processes, there'd be many more events, but in this very simple case, we can work out what the critical path is. And the way in which that's done is actually working backwards from the last event. There's no critical path where there's a wait state, so it's where the last computation takes place, in this case in the middle process. And then the communication that preceded that is where we transfer the critical path to, in this case, the process at the top. So the process at the top, when it is executing var, is on the critical path. And then when the event before that, when it was doing the receive, transferred the critical path to where that corresponding message was coming from. In this case, it was the process at the bottom that was executing foo and then executing the send. So that was allowing us to reconstruct the critical path of execution through these events. And the key thing to note is that the events on the critical path are the ones that determine the total execution. We could remove the events on the other process, we could make them zero size. All that would happen is there'd be more waiting time until the events on the critical path are completed. So until the send on the bottom is initiated, all of the other processes have waiting time. That means that they're not critical. Likewise, when we're in the middle executing bar, it's only the part of bar in the middle executed on the top rank that determines the critical path. Bar, as we can see, is executed by the other ranks as well, but the other ranks don't in this case contribute to the critical path execution of bar. It's only the time of bar on the top rank that that contributes to the critical path. And so those are the things that going through going through the execution trace, examining the relationships, the correspondences between these events allows us to determine where the critical path actually is. And by figuring out that and focusing on that, that's where we can concentrate optimization opportunities, optimization activities. Knowing where the critical path events are is a good starting point, but we actually are more interested in what was causing the delays on the critical path, and that's the next step of the analysis here. That's the root cause analysis, where we're trying to figure out what computation was executing that was imbalanced or taking longer and delaying the fact that the corresponding sends had to be couldn't be initiated until at later points of the execution. So in this case, we're seeing a fragment of the execution where the top process is executing through, is taking longer for some reason, and the part that takes longer is an indication that there's some imbalance or some other activity going on that is delaying the top rank here being able to initiate its send. And because it's delayed in initiating the send, in this case to the middle rank, that means that there's a delay on the middle rank. It's having to wait until the corresponding send from the top process is initiated, and likewise there's a chain of events that subsequent send operations are delayed from the ones that were incoming events to that middle process. So there's a chain of delays which are either directly related to the events that are being received, or they're indirect because they're related to events on other processes that were delaying them before they could initiate the communication that the process at the bottom in this case is dependent on. So by determining these chains of interactions, we can characterize and quantify what are the delay costs, the additional computations on the different processes and threads that determine the ultimate execution time. So that's what we're going to be looking for in our trace analysis. I'm going to quickly move on, and we'll start by seeing how we can use Scalaska for this on Archer. This was a continuation of the set of steps that Christian introduced this morning, where we saw that we've gone through the basic instrumentation and preparation of the application. We've done some scoring and filtering to optimize the measurement configuration and get us to an execution configuration that is more optimal, more appropriate for not only for summary measurement analysis, but also for the trace analysis. So I'll quickly review that before we go on. But ultimately, we'll use the same executable and then continue with the part at the bottom here, which is looking at the trace collection and the trace analysis. So there's one additional command that we're going to introduce to you. That's the Scalaska command. You can think of it as one command for almost everything. It used to do all of the steps of instrumentation analysis and measurement examination, but we've already seen that now you can use Scorpio for the instrumentation part. So that's what we encourage you to use there. But for the other two parts, for actually running the application and controlling the measurement, we would use Scalaska Analyze, and then for the subsequent exploration and processing of the measurement, we would use Scalaska Examine. There are a couple of shortcuts for these commands. So Scalaska Analyze, we also refer to as scan. Scalaska Examine, we shorten to square. And you can use those commands interchangeably. One's just an alias for the other. So this Scalaska Analyze command, or the scan command, is our collection and analysis nexus for measurements. It's like we saw with Scorpio, it's a preposition for the launch execution command. So whereas you use Scorpio as a preposition for the compile and link commands, we're going to use scan or Scalaska Analyze as a preposition for the launch command, for the MPI's exec, or in this case, for the AP run command. It takes various options which allow us to determine what sort of measurement and what sort of analysis we're going to do, but it's going to particularly look at the launch configuration, and from that it'll figure out how many MPI processes we're working with, how many threads we're working with, and it will use that to configure our measurement configuration, set an appropriate experiment name for us, but more importantly, it gets us in a position where we can actually launch and redo the trace analysis, which is going to be the second stage. Just to quickly mention the square command at this point, the Scalaska examine will do some post-processing. We'll see an example of that. It's just a convenience for calling cube. You're certainly able to use cube directly as an alternative, but the additional post-processing will allow us to do some things a little bit more conveniently, and particularly get some additional metrics which can be useful for augmenting the analysis. The reason for using the scan command instead of just running things directly, which you can certainly do, you can configure everything through environment variables, as was mentioned this morning, but there are some things that the scan command will do as a convenience for you. It will figure out an experiment title based on the execution configuration, which can be convenient. And if there's a filter file involved, it will be saving that. It will be saving some other information from the execution configuration, just so that you have everything conveniently stored in the same measurement directory. As part of that, it's going to be doing a few consistency checks based on the launch configuration, so it will prevent the corruption of an existing measurement directory. If you try and do a measurement, a new measurement while Scorpio already has one active, then it will end up corrupting it, and then you'll end up with some problems. Either the measurement that you initially wanted will be corrupted, or the new one that you're trying to collect will be corrupted. So the scan command is going to be checking that and avoiding that situation. It'll also do some other checks to see that to make sure that the measurement configuration is appropriate for what it's going to do. But as I mentioned, the key thing is that by looking at the execution configuration, we're ready to do the trace collection and trace analysis as part of the same execution configuration. The same scan command can be used to relaunch the trace analyzer in the configuration which will be used for analyzing the trace. It will, of course, check that the trace was collected as part of the initial measurement, and when that is appropriate, it will launch the trace analyzer as a subsequent step automatically, so that it's, again, using the same resources as part of the same job. So you've already seen and are hopefully familiar with the execution configuration on Archer. We're using the Scalaska module, which loads Scorpion Cube, and we're using the BTA example, which we saw earlier, and which has already been prepared for our measurement. We already have it instrumented. We already have an executable in the directory ready to run. We already saw how we can do a measurement and some filtering and scoring of that measurement with Scorpio. The first thing I'll do is I'll just redo the measurement in my directory with the Scalaska analyze command. So we'll see that, and then that will have us ready to see just how the process changed. And as you can see here, what we're doing is we're setting the Scalaska analyze as a preposition to the previous AP run command. So let me switch to my terminal session so that I can run this. Share. Hoping that you're now able to see the directory where we already have an initial Scorpio measurement, and we already have the output there. There's a job script provided for Scalaska for Archer, so I'll just copy that into the current directory and take a look at what it contains. I'll uncomment the queue so that we can run in that. We're loading the Scalaska module in the job script as well, because we're going to be using the Scalaska analyze command. That's what we're seeing here at the bottom of the screen. We're using Scalaska analyze as a preposition for the AP run command, which we would be running otherwise. I can leave everything else uncommented, and then I just get a default measurement. But we already saw from the earlier case that using a filter file is a good thing. So setting the environment variable for that is a good thing to have. I can set an experiment directory name, but since Scalaska Analyze will do one automatically, I'll leave that out. And in principle, we have a few other things that we can set here. Maybe it's useful to have some hardware counters. So there's an example here of 2-3 hardware counters that we can also add into the measurement, and we'll see those as part of the measurement that I get as well. So if I run that Q subcommand, hopefully it will run in just a moment. The key thing to note was that I loaded the Scalaska module. On Archer, there's a number of Scalaska modules available. The one which I recommend, the one which is set up with the latest version of Scorpio, is the one which is on this additional module path. So it's not the default module, which is using an older version of Scorpio, but it's a newer version. So if you want to use the newer Scorpio, make sure that that you have these modules added to your path. On other systems, look for the appropriate modules and have them there. Versions of Scalaska correspond to the different compilers or the different tool chains. In this case, I'm using the version for the GNU tool chain. If I was using the Intel compilers or the Cray compilers, I would have a separate tool chain for those. And it's also important to make sure that, especially with Scorpio, that you have the appropriate Scorpio tool chain matching the compiler, matching the MPI that you're running with. When it comes to the Scalaska trace analysis, things are a lot less strict. And actually, in most cases, the GNU tool chain is the one that I would use for the Scalaska trace analysis, irrespective of which version was used for Scorpio and for measurement collection. So I think that our measurement is done or almost done. It seems like it's done. And what we see here is that it created a new measurement directory. This time it actually included the name of the executable. So it took the brief executable and included that automatically in the name of the experiment directory. And it also included the measurement configuration. This is the number of MPI processes times number of OpenMP threads, 8 times 6 in this case. And because it was a default measurement, a summary measurement, it automatically used an underscore some suffix for that. Inside that directory, we'll see the same sort of material that we saw before. We have a manifest, we have a profile that was the interesting part, we'll look at in a moment. We have the measurement configuration as recorded. We have a copy of the filter that was used. And we also have a copy of the execution log. So that's in the job output automatically, but just for convenience, it's also stored here in the measurement directory as well. So inside here, I have a record of the command that was used and how long it took to do the measurement. In this case, it's 22 seconds. The main reason that this is different from the Scorpio measurement, which I have above. So in my initial Scorpio measurement, it was around, this was the unfiltered version, so I can't do the comparison there, but the reason it took a little bit longer is because I included hardware counters in this measurement. So if I was to just check that in the Scorpio configuration, see here the hardware counters that I configured, as well as the fact that I explicitly, or the Scalaska Analyze explicitly configured an appropriate measurement directory name for this. If for some reason I was to resubmit this Scalaska job, it's going to tell me that there's a problem because this directory already exists here. So because that directory exists, it's going to tell me that I would need to rename it, move it, give it a different name, or give it rename it explicitly in the Scalaska scan command, just so that I avoid a conflict there when the new job runs. We'll see that when it comes to it in a moment. The other command which I want to show you here is the other part of the basic Scalaska command. So this Scalaska examine, or the square command. So I'll just use square as a shortcut. Square takes the name of the experiment archive as an argument here. So that's where I would give it the name of the new measurement directory that I collected. I could use the previous one from Scorpio, as long as it has a Scorpio profile or Scorpio measurement inside it, I can use that. And the first thing it does is it does some post-processing of that initial measurement. So we only store summary or very basic metrics in the profile. By doing some additional post-processing, we can derive additional metrics, and those are what I'm going to show you in a moment when it's finished here. What the square command is also going to do once it's finished is it would try and launch the Cube GUI. That's not going to work for me remotely because I don't have X forwarding. But again, I have a copy of this this measurement on my laptop already copied, so that's the version that I'm going to add. So it post-processed the profile CubeX into the summary CubeX here, and it's stored that in the directory. So this was the initial profile. This is the summary that was generated from it. If we can compare the sizes, the summary is quite a bit larger because it has a lot more metrics that have been derived and added to the profile, to the summary in this case. So what's the added value? What are we seeing in addition there? So I need to stop sharing this one. And let's get my new measurement. And this was my session here. Okay, so this was the initial measurement we had earlier. I'm just going to switch and open the new one that I already have. This is the one that Christian showed you with the filter file applied. I'm going to go up one directory here and look at this summary measurement. There's the initial profile. That initial profile is very similar to the one that we saw before. It has the filter applied, so it doesn't have the same measurement overheads to it. And that also means that if we dive down into these solve routines, previously we were seeing inside here were additional routines. Those additional routines we filtered out, and so they no longer appear. We don't see any time for them. We don't see any count for them. All of the time for them has been attributed to the parallel do loop itself in this case. and the same for the other solve routines here as well. So we're no longer seeing a lot of the fine detail, but we're seeing, we're seeing the high-level detail like we had before. We're seeing the MPI communication, we're seeing the barriers, the reduction operations, everything as before. I added 3 hardware counters, so we're also seeing those here on the left-hand side. The hardware counters just appear as no metrics. So just like we have the number of visits, we have the number of bytes sent, received, read, and written. We also have the hardware counters here appearing as additional metrics, and we can see, in this case, the number of resource stalls, how those are distributed across the application call paths, and as before, for each process and for each thread. That's the basic Scorpio level information, the basic Scorpio profile with these additional hardware counters added. But what I want to show you is this summary file, which is a little bit larger and has the same information, but it has it augmented. So at first glance, it should look very similar. What we see in the middle should look almost identical. What we're seeing on the right-hand side is identical. What has really changed is what's happening in the left-hand side in this metric tree. For one thing, it has reordered the metrics, it has restructured the metrics. So we still have the metrics we had before. We still have the hardware counters that we had before. We still have visits. We have bytes sent and received. They're shown in different places, but they are in the same hierarchy, or the same metrics are there, but they're put into a different hierarchy. The key change is in this time metric. Previously, we just had execution time, CPU time, and we could see where that was in the application call tree, and we could see which processes and threads that was distributed over. So in this computational kernel, the benchmark here, the different threads are taking 21.5 seconds in this case. But by additional post-processing, we can derive additional metrics. We can split the execution time into what is purely computation time versus time in MPI operations or time in OpenMP constructs. And consider this the OpenMP runtime overhead in this case. If we look at the proportion of time here, it's telling us this is 14% of the total time is in this OpenMP runtime versus less than 0.5% of the time, which is an MPI. No particular surprise in this case, we're not using very many MPI processes. So actually most of the runtime overhead in this case is for OpenMP. It's in our computational kernel, and we can see just the OpenMP overhead for the solver routines, for the parallel loops, which have the solver here. So what it's showing is not the time in the do loop, but it's showing the time in the implicit barrier, or if there was explicit barriers or locks coming from OpenMP. That's what this OpenMP overhead is looking at. OpenMP synchronizations, barrier synchronizations, and in this case, the implicit barrier synchronizations. There's not an explicit OpenMP barrier, but we can see what proportion of the total execution time is implicit barrier synchronization, and we can see how much of it is in the 3 kernels we have here, and also in other more complex parts of the code as well, where there are more things going on. So that allows us to see more or less at a glance where barrier synchronization is an issue, and that's going to be related to computational imbalance, which is coming from the preceding computation. In this case, on the right-hand side here, if I switch the presentation mode, we're seeing the variation in in computation time across the different threads as compared to the time not in the critical, in this implicit barrier synchronization. It's telling me that we have a very small amount of OpenMP critical time. I can easily find out where that is just by looking for the colors here. This red part here shows me that's where most of it is. And I can see that it's in this verification part of the code. That's where there's an OpenMP atomic in this case. There's also another one as part of the calculation of the norm here. So where there are critical sections, where there are atomics or other locks being used, again, those show up as explicit inefficiency metrics here as part of OpenMP. And by going through this hierarchy, we can find out their relative cost, and we can identify where they occur, and we can figure out at a glance which processes and threads are most affected by them. And by seeing not only the time in the atomic, by looking at how often it's executed, we can see in this case that every thread is executing at the same number of times. In other cases, there may be differences across the threads which are important. That was the OpenMP metric hierarchy. For MPI, we have a similar hierarchy where we split the MPI time into time for management operations. So this is the initialization and finalize here. We already saw the initialization earlier. Maybe there's some communicator management here. None of this is very significant. Synchronization here for collective operations identifies where there's barrier synchronization. Communication is split into the point-to-point part, which is what we were explicitly doing inside the kernel itself. So that's where we have sends and receives here. The time in the wait hole is shown differently as part of the request handling. So that's request completion, because that can be not only for point-to-point operations, it could also be done for non-blocking file I/O or non-blocking collectives. So all of those are, for us at the moment, difficult to distinguish. They all are completed by the wait hole operation, and that's why they're showing up as request completion in this case. For the collective communication, we see the time in the reductions down here at the end. I think those are the only collective operations which this code is doing. So there's various things going on here at the MPI level. In this case, we see at a glance that they're not very significant. It's only a very relatively small proportion of the execution time. But if we were to run this code with more processes and fewer threads, or run it on more nodes, we would see that the MPI proportion of time would increase, and then we'd have more reason to explore the MPI execution behavior in more detail. We saw in this case that there's OP time, which is significant. This is OpenMP runtime inside the parallel loops. There's another metric here which is called idle thread time. That's also related to OpenMP. Whereas the time here is the runtime for the parallel loops and what's happening inside the parallel loops, the atomics, the other synchronizations. These idle threads here are our way of accounting for what's happening outside the parallel loops. So if I back up a little bit here, when we look at the execution time, we're seeing there's a execution time in a parallel loop here on the different processes and threads. If we go inside the parallel loop, we also see every thread is involved in that computation. There may be cases where it's not, but in general, the parallel loop is executed by all of the threads. But what's happening outside of the parallel loop, and if I go up the call tree to here compute a right-hand side or this ADI routine, this is only executed by the master thread because it's executed outside of the parallel loop. The implication is that the other threads which have been allocated for this application's execution, the additional cores, the additional resources, are not being used other than when we're inside the parallel region here. So when we're outside the parallel region, we have no execution time on those threads, and that's accounted for here as idle time. Think of it as idle cores, idle threads. It's time where resources are not being used and we're outside of a parallel region, which is the explanation for it. It may be that we're actually inside the parallel region, but not all of the threads are active, and we see some cases of that as well, but that's a much smaller consideration here. In most cases, when we're inside the parallel region, we're using all of the cores, but when we are outside of the parallel region, those cores are idle and those are not being used. That idle time which we're seeing here, let me go to absolute times, maybe go back here. I want to get up a bit here. This idle time which we're accounting for on the worker threads, the non-master thread here, corresponds to what the master was doing outside of the parallel region. So if I was to look at the execution time, some of that will be for the master thread. And so here we have time which is only executed by the master thread, and if we look at the corresponding idle time, that same time is being attributed as idle time on those other threads. It depends on which process I'm looking at, so that's why down here the idle time is different. On rank 0 it's a little bit higher, but whatever was execution time outside of the parallel region on the master is idle time for the corresponding worker threads. So that's why these numbers match the corresponding master thread number. So all of these metrics are documented in the online documentation. So if I was to look at the point-to-point metric here and look at the documentation for it, we'll see that later. It's not working here. So what was I wanting to show here? Basically, we took the aggregate time, we split it up and generated this hierarchy, which allows us to see the different components of it, the parts which are related to MPI, the parts which are related to OpenMP, the parts which we consider to be idle time. We did more of an overview of how that time is broken down and where it occurs in the application. For the other operations, such as the bytes transferred, again, we have a hierarchy that allows us to split what is collective time from what's point to point, what's send and receive, etc. So that additional hierarchy we're seeing here for the basic profile, we'll see it in a moment how it gets expanded even further in the corresponding trace analysis. So at this point, I want to go back to my slides, share what I was looking at before. Share slides. Where was I? Okay, so this was where we'd reached to before. We'd basically just done the same measurement as we saw this morning with a filter file, adding a few hardware counters and seeing those in the measurement. We're basically getting everything that we would have before in a slightly more convenient way through the Scalaska analyze command. If you prefer to set things manually and augment things manually with Scorpio, you can do that as you prefer. We saw how when it ran, we got some additional commentary about what it was doing and the measurement directory it was using, just to have an idea of what we were doing as it was going on. And I didn't run the square-s command, but it's the equivalent of the scoring command which we saw earlier, that doing the square-s on the measurement directory would create the Scorpio score file and store it into that directory itself. I showed you the square command, which did the post-processing and then presented the new measurement directory. The square-s also does the post-processing, so if you're on Archer, you may want to run that on Archer and then just copy the summary cube file that's generated as a result of that to your workstation to look at. Otherwise, you won't have these additional metrics as part of that when you just have cube on your laptop. And we saw the additional hierarchy, and we saw the metric presentation. So so far so good, more or less revision of what we saw earlier, but now we're ready and in a position to quickly move on and do event trace collection and analysis. I'm going to go back into the same job script which we were looking at before. I'll run the scoring when I remember it, and then we'll set the trace buffer size appropriately, and then we'll run a slightly different version of the trace analyze command, or you can set the Scorpio enable tracing environment variable to do the trace collection and analysis. So I'm switching back and forward at this point, back to my terminal session. Okay, so I'm back on Archer looking at my at the directory where I was before. While I remember it, I'm just going to run the square-s command on the measurement directory. Quickly this time because it was already processed. But now when I look inside the directory, I have the Scorpio score detailed breakdown is already there, telling me that I need to be prepared for setting a buffer size on each process of 95 or 100 megabytes in this case, confirming everything else is as I would expect using the filter file, but I need to make sure that I have 95 or 100 megabytes of trace buffer size for the trace collection. For the profile collection, it's not important, not so important at least. The trace collection, I would need to make sure that I reserve roughly 100 megabytes. So now when I go into my job script, the same job script as before, I'm going to continue using the filter file. Without that, I would have huge memory requirements. I'm going to uncomment the line telling it to use the total memory of 100 megabytes per process. I would need more memory if I wanted to collect the hardware counters, but I'm just going to comment it out in this case because we're not going to analyze as part of the trace analysis, so I don't need those in the trace itself. As I said, we could set the environment variable to say I want to do a trace measurement, or I can use the appropriate switch here for the trace analyze command, saying that it should do the trace collection. As well as doing the trace collection, we'll see it does a little bit more. But let me get that started. I didn't change the name of the experiment directory because I changed the configuration to be a a trace measurement, it will automatically give the new measurement directory a different name. And hopefully it starts soon. So we see it's already started, and as soon as it started, as part of the MPI init, it will create the measurement directory. And inside that directory, it won't actually contain very much at the moment, because it will only produce the traces and the profiles at the very end. But it's already finished, so we're already in a good position here. We see that it has created a subdirectory here for storing the traces, and then this is the OTF anchor file, which we could use for looking at the trace that was collected. I still have a profile here because I didn't disable the profile collection. If you want to disable that and just look at the trace, that's fine, you can do that as well. In this case, I'm now more interested in the trace, so that's what we'll look at in a moment. The job is probably now finished. It's actually just finishing. It took a bit longer this time because after the trace collection, which finished a moment ago, it went on and did a little bit more work. And so if I look in the directory again, I'll see it's produced a few more files now. The main file that it has produced is this scout.cubex file, the scout.log file. That's the trace analyzer that we're using. The Scalaska trace analyzer is known as Scout, and so the raw output that it produces is called scout.cubex. When I look at the job output itself, so this is for job 389. So the last job that I ran. So this was the Scalaska analyze command running. It's telling us that it was doing a trace collection and analysis and the directory it was putting it into. The first thing it does is it runs the application with the environment set up to collect that trace data. Execution time is down again to 21 seconds, so that's good. And at the end of that, it reports that the trace collection is complete. So it has, at the very end in the finalize, it has been writing the trace files to the disk, and those are in that traces subdirectory that I briefly showed you. It immediately continued and started the trace analysis. And to do the trace analysis, it's using the same AP run configuration, the same number of processes and the same number of threads and cores per process, but it's starting the trace analyzer. The Scalaska trace analyzer, in this case, is called Scout, and it's starting and looking at the traces which were automatically collected. It's giving a report here in this case about what analysis it did, but then it's completed that analysis. In this case, it took 38 seconds. As I said, maybe it's a comparable time to the initial measurement collection. Maybe it's a little bit slower, maybe it's faster in some cases, roughly the same order of magnitude. And then our trace analysis is complete. We're seeing here the trace analysis is the trace data, the raw trace data is still there. We still have our 540 megabytes of trace data is retained here. We could take a look at that with Vampire or one of the other trace visualization tools, but we're particularly interested in the automated analysis that came from Scout, or the Scalaska trace analyzer, which is now in this file here. Again, I would use Square to do the post-processing of this. I give it the directory, it will post-process all of the files that it contains in there, so it's going to post-process this profile as well as the Scout file, and then we can take a look at what's in the Scout file and in the post-processed version in particular. So I don't think there's anything more that is interesting to see here. Maybe I'll just quickly show you the trace data itself. The files are not very interesting to look at, but just to show you that they're in this traces directory. There's one per process, and there's additional definitions. So this is pretty large. You don't need this on your laptop when you're looking at the cube files there. So just if you're transferring cube files, just transfer those rather than transfer the raw trace data itself. I need to switch to my cube now, which is here. So this is my my trace measurement that I'm going to open. Inside that directory, I now have 4 files. I have the initial raw profile produced by Scorpio, which gets mapped into this summary file, which is a factor of 10 larger. I have the raw metric file from Scout, and then I have the post-process version, which is about twice the size of a summary file in this case as well. So that's already indicative that there's additional metrics being produced in this or presented in this trace analysis file. If I just quickly look at the Scout output, we'll see a whole bunch of very low-level measurements about these metrics I was referring to: early sender, late sender, early scan, receive, etc., OpenMP critical contention. All of those metrics then get post-processed in the post-processing. So when I look at the trace file, the trace cube file, again, I'm just seeing one metric here at the highest level for time, but I can go down through the hierarchy. Hierarchy at the top level, again, looks very similar. Only a small percentage of time in MPI, 18% of the time in OpenMP in this case. But if I expand these hierarchies further, perhaps you can see that there's some additional highlighting here, which is indicating that there's additional metrics coming from the trace analysis. So it's telling me that of the 6 seconds of time here, which is in point-to-point communication, most of which is in the wait hole down here, it's telling me that 3/4 of that is actually late sender time in the wait hole, obviously. And if I was expanding the right tree, I would see which processes have more waiting time than others. In this case, I can see that it's primarily rank 0, 1, and 4 have 4 and 5 have higher values. There's relatively little waiting time on rank 2. So that's an indication that rank 2 had more computation or took longer and then had less waiting time when it came to this point-to-point communication. If I resize this a little bit, maybe we get a little bit of explanation of these metrics. So the documentation here is explaining this hierarchy, that as I go down from time through execution time, the component of the time which is MPI, the part which is MPI communication time, and then the proportion of MPI communication time, which is part of the hierarchy which is related to point-to-point communication, and then the fraction of the point-to-point communication time, which is, in this case, broken down into these wait state metrics, the late sender time, explaining what a late sender is, or late receiver, where it's the receive that has to wait for the corresponding send to be initiated. So we have explanation of the point-to-point metrics. There's explanation of these collective metrics, showing the waiting time on the root of the reduce, which has to wait for the corresponding other processes. For a scan, a subset of the processes have to wait a broadcast, etc. So there are examples documenting and explaining what these different metrics refer to. I mentioned the idle threads time. This diagram here is an attempt to explain that, where if we think of this as the execution timeline, where we're seeing 4 cores. When we're in the serial computation outside of the parallel region, we have 3 of those cores that are idle, shown in red here. When we enter the parallel region, in this case, we're only using 3 of the cores. The 4th core is idle. And then when we complete the parallel region, we're back into serial execution again. Again, we have idle threads, idle cores for the remaining time. So in this case, we have idle thread time where there's these red lines being shown, and part of that is limited parallelism time. That's just the part where we're inside the parallel region, but we're not actually using all of the threads. In this case, perhaps there was a loop with dimension 3. If there's a loop of dimension 3, it can't be parallelized over 4 cores, and so one of the cores is going to be idle. If you have more cores, you're going to have more idle there. But in most cases, parallel regions are typically executed by all of the threads within them. So those were the time metrics. We also saw the hierarchy was expanded with additional metrics showing, for example, the critical path. So we saw the explanation of the critical path earlier, where process 2 starts on the critical path, and then the communication to process 0 transfers the critical path to rank 0, and then to rank 1 here at the end. This is just a diagram. If I go back into the metric itself here we're seeing what proportion of the execution time is on the different call paths on the different processes. So the length of the critical path is our 21 seconds. That's to be expected from the total execution time on each thread. So they're all roughly 20.8 seconds in this case. So the critical path is going to be 20.8 seconds. It doesn't match exactly because the critical path is only calculated between the MPI init and the MPI finalize. But where is that critical path? Most of it's in this ADI routine down here, and we see it's mostly on rank 2. So it's already identified rank 2 and the execution on rank 2 as being the critical path, as being the key to the execution here. If we go down further, we see how it's split into the X, Y, and Z solve. And again, we can see what proportion of that is for rank 2 versus other ranks. I think it's almost always rank 2 in this case. It can move around. It depends on your application. But for an application like this, which is SPMD, all the processes, all the threads are executing, if not exactly the same or very similar execution call path, the critical path tends not to move around very much or move between processes very much. And then having identified where the critical path is, we can take a look at what costs are deriving from that. And so we're seeing the additional delay costs, where those are coming from, and which threads they're responsible for them. Here it's the master threads that's showing up as the main cost, because it's executing things outside of the parallel loop, which of course if it's not executed in the parallel loop is an additional cost for the master processes. We will also see where all of this communication here, or the communication here, all of that is an additional delay cost, which manifests on the corresponding master processes, master threads in each case. Relatively little of the delay cost is due to the MPI itself. It's in this case arising from imbalances in the OpenMP, where some of those imbalances are waiting at barriers, or they're related to idleness in the computation, whether it's an immediate delay or whether it's a longer-term delay from something that occurred rather earlier before the actual routine that initiated the communication. So there's a lot of complex metrics here which can give you insight into where the inefficiencies are in your application execution. We saw in the presentation yesterday that sometimes it's good to start with a rather higher level perspective. Such a higher level perspective is available from what we call the advisor here. So just like with the X-ray traces and with Paraver, you can get an assessment of what the overall efficiency of the focus of your analysis is. We can calculate that here and give you at a glance an overview of what sort of efficiencies you have for this, for either the entire computation here or just for the part that you're primarily interested in here. So the computational benchmark here, it's where most of the time is. So in this case, it doesn't differ very much, but we see at a glance that the communication is pretty efficient here. There's a certain amount of serialization efficiency here related to the fact that we have computation in computation outside of the parallel sections, or only executed in atomics within the parallel regions. We have also load balance here across the processes, across the threads. That's the higher or the most severe inefficiency here. So that's the key thing that you would look to optimize to improve the overall efficiency of this application execution here. So the overall execution efficiency 0.78 is not so bad. What you'd of course want to compare is how it changes when you run it with more threads, run it with more processes, run it on more compute nodes, run it on more compute nodes. How do these efficiencies change, and in which aspects do they change? If you find it's a load balance issue, you probably want to figure out where the computational imbalances are, using, for example, one of the presentations here, which gives you a view of how that computational time is spread across the processes and threads, perhaps by looking at things in this topological perspective. Alternatively, if you find that it's an OpenMP synchronization issue, you'll want to look at where the OpenMP synchronization costs are most severe, which again we're seeing here. Or if it was an MPI issue, you would look at, is it related to collective operations, or is it barrier synchronization, is it point-to-point communication? All of those metrics you can then use as a focus for deciding what's going on, where the time is spent, how much of that time can be explained by differences in the amount of data that's being transferred, or the number of times it sends and receives are done, and how those vary across processes. So all of those metrics are available through the same interface, and this GUI is set up to facilitate the exploration of those, to allow you to get a high-level overview, but then to dive down and see in detail what's happening, which parts of the program are responsible for this, and which processes and threads are affected or contributing to it. I think that's everything that I wanted to show here. So I'll quickly go back to my slides. We're already past this part. We already went through the trace collection. So I showed you that as part of the Scalaska trace collection with the Scalaska analyze, we capture the measurement output, and then we initiate the trace automated trace analysis that's done immediately afterwards, and then we get an additional analysis file that we can look at, and which we just explored. And we see then the additional metrics in the metric hierarchy. I don't think I need to go through these slides again, so I think that we are pretty much complete for now. Just to summarize, the Scalaska trace tools facilitate the trace collection and analysis, particularly the automated analysis, providing additional insight into the inefficiencies of communication and synchronization of your parallel applications. It's designed for scalability and to be able to handle very large scale systems, whether we're dealing with a few nodes or very large collections of processes and threads, supporting MPI, different forms of threading, and particularly the hybrid combinations of MPI and different threading together. For more information, for downloading the sources and information about how to install the tools, I refer you to the Scalaska website. And if you have any questions and need additional assistance, we have the Scalaska mailing list here, which you can contact and which we would respond to. This is also the same mailing list, by the way, for Cube, if you have any questions or issues related to the Cube GUI. You can send Scorpio questions there as well, because we use Scorpio a lot, but there's a separate mailing list which will show you for that. I think at this point I can switch back to you, Christian, and you can finish up with some of the more specialized aspects of measurement collection.
Yes, but so it's already 12, I think, in Edinburgh. So usually the break is scheduled for now. So I can do another 15 minutes for the additional Scorpio features, or we can do this when we come back from the break. So what is the opinion in the audience? Shall we do another 15 minutes?
If it's lunchtime, it's better to keep to the lunch schedule, and then we'd restart in 90 minutes. I hadn't realized how much time we'd use. So we have a few more slides that we can present, but we've covered the basics. It'll be a short presentation when we reconvene after lunch, and then I think we're ready to help you if you want to try and use the tools with the BT exercise which we provided, or if you want to try and apply them to other codes that you have built and running ready to analyze on the Archer system. And then there's another TAU session later this afternoon as well. But I think it's good that we finish here, and then we'll restart in 90 minutes, which is 2 p.m. in the UK, 3 p.m. for us in Central Europe.
Okay.
Cedric, is that okay with you?
Yeah. Okay, let's start in at 2 p.m. or 3 p.m. in Europe. Yeah, fine. So thank you, Brian and Christian, and we'll return in 90 minutes.
Okay, bye.